Good morning, dear students. Today we are going to start with the next topic of the solid state, that is lattice, unit cell, and packing. In this topic, we will see different type of unit cell, primitive and centered, and their classification. Then we'll see how the particles show the packing in one dimension, two dimension, and three dimension. And due to that, how many types of void and what type of voids are obtained. Let's see. So, up till now we have discussed about the four types of the crystalline solids that you know very well, and they are molecular solids, ionic solids, metallic solids, and covalent solid. And we have discussed the molecular solids are classified in further into three categories: non-polar solids, polar solids, and hydrogen bonded solid. I hope this is clear to all of you. Now we'll see crystal lattice and unit cell. When we talk about the crystal lattice, regular arrangement of points in three dimension is called crystal lattice. These points are called the lattice point. So you can call these points as the lattice points. Total 14 possible three-dimensional lattices are possible. In your NCERT, one table is given for the Bravais lattice and their structures are also given. We'll see in the next slide also about their structures. But details are not there, so you only go through once. These are called the Bravais crystal lattice. Now unit cell, smallest portion of the unit crystal which is repeated in different direction and generate the entire lattice called the unit cell. In my previous video I told you about the unit cell and the comparison with a brick and a wall. There also I have given you the example that imagine the unit cell is a brick. So with the help of the brick we can form a wall. So repeatedly when the bricks are arranged in a particular direction, then you can see whole wall can be obtained. So this wall is known as the crystal lattice, but this particular single brick is known as the unit cell. There are four types of the unit cell and their classification also we have done. These four types of the unit cell are primitive, also called as simple cubic cell or unit cell SCC, body centered BCC, face centered unit cell FCC, and end centered ECC. This ECC is not in your course. So in this chapter we are going to discuss about three unit cell: SCC, BCC, and FCC. When we talk about the primitive or SCC, in this the constituent particles are present at the corner. So you know in any cube 8 corners are there. So you can see the particles are present at the corner only. So this is known as the simple unit cell. Body centered unit cell. In body centered unit cell, constituent particles are present at the corners. So 8 corners are there as we have discussed in SCC. Along with this, one particle is present at the center of the body. So along with the corners, one is at the center. This is known as the BCC. FCC, in face centered unit cell, particles are present at the corner. So you can see 8 particles are there at the corners. Now one particle is present on each face. So this is the upward blue color, downward at the center, right side, left side, back side, front side. So 6 faces are there. So 6 more constituent particles are present on each face. Last one is the end-centered. In case of the end-centered, the particles are present at the corners. And along with the corners, 8 corners, at the two end, you can count it left, right, you can count it back and front, or you can count it at the top and the downside. So here you can see it is at the this end red color and this side upside and downside. But this end centered is not in your course, so we are not going to discuss much about the end centered. So these are the definitions for the primitive and centered unit cell. So first one is the primitive unit cell, which is also known as SCC. We have discussed particles are present at the corner. So when the constituent particles are present only on the corner position of the unit cell, then it is called primitive unit cell, or also known as SCC. Then second is the centered unit cell. When the unit cell contain one or more constituent particles present at the position other than the corners, in addition to those at the corners, it is called as centered unit cell. And centered unit cell are classified into 3 more: BCC, FCC and ECC, out of which we are going to discuss about BCC and FCC. Body centered unit cell. In such a unit cell contain one constituent particle at its body center besides the ones that are its corner. Means particles are at the corner as well as one is at the body center. In face centered, such a unit cell contain one constituent particle present at the center of each face. We have seen this in diagram. Beside the ones that are at corner, means particle are at the corner as well as on the center of each face, and 6 faces are there. In end centered, constituent particles are present at the center of any 2 opposite faces along with present at the corners. So these are the 7 main lattices by which we can form 14 Bravais lattice, in which one is cubic. Mostly we are going to discuss about this only. Tetragonal, orthorhombic, hexagonal, rhomboidal, monoclinic and triclinic. And their distinguished features are on the basis of their angle alpha, beta and gamma, as well as their side A, B and C. Now number of atoms in the unit cell. For example, if you are in 12th A and in your class about 65 students are there, so your contribution toward your class is 1 by 65. Similarly, whatever the constituent particles are situated, their contribution towards the unit cell or towards the crystal. So here we are going to discuss about how many number of atom in the unit cell. A primitive cubic unit cell, only 8 atoms at the corner. Clear? So if 8 atoms are there, then their contribution towards the unit cell or lattice will be only 1/8 of the atom. Each small sphere represent only the vertex and not the actual size. So such structure are known as the open structure. So when we talk about the contribution of the primitive unit cell, 8 particles at the corner, contribution will be 1/8. So number of atom in the unit cell will be 1. Body centered cubic cell, in this you know very well. You can see the different diagrams. This is the crystal structure diagram, first one. This is the actual the particles arranged, and this is the bifurcated one. So in case of the body centered, as you know, 8 particles are at the corner. So their contribution will be 1 by 8 like the primitive, plus 1 particle is at the center. So this center particle, you can see this center particle. It is touching all the constituent particles present at the corner. So its contribution will be 1 for all. So total contribution will be 8 into 1 by 8 plus 1. That is 2. Total number of atom per unit cell will be 2. Face-centered cubic cell. In case of face-centered unit cell, it contains atom at all the corners and the faces. So if the particles are at the corner, so their contribution will be 8 into 1 by 8. That is 1 for corner 1. And for faces, for example, if you imagine any cube. So if any particle, like the particle at the top, this particle is representing for the top portion also and for the bottom portion also, because it is 3-dimension view. So this particle is having the contribution of half for the upper one and half for the lower one. So 6 faces are there and the 6 particles are contributing half. 6 faces and contribution is half. So total contribution per unit cell will be 8 into 1 by 8 for the corner and 6 into 1 by 2 for the faces. So total contribution will be 8 at cancel 1, 2 and 3 cancel 3. 1 plus 3, that is 4. So total number of atom per unit cell will be 4. Here you can see the diagram of FCC. Now we'll discuss about the packing. Packing can be done in 3 ways, either 1 dimension, 2 dimension or 3 dimension. When we talk about the 1 dimension packing, then you can arrange the constituent particle in this way only. So if I will take any particle, for example, I am taking the third particle. So how many more particle is touching this blue particle? Obviously 2 more particles are there. One on the right side and one on the left side. So in this case, the coordination number is 2. In this, each sphere is in contact with the 2 of its neighbors. The number of nearest neighbors of a particle is called its coordination number. So here coordination number is 2. In 2-dimension packing, the arrangement of the particle takes place in 2 ways. We call it as hexagonal close packing or square close packing. So when the rows are combined, touching each other, the crystal plane is obtained. The rows can be obtained in 2 different ways, as I told you, in which AA type of arrangement is there. Then you will get the square close packing. We will see the diagram. And if AB type of arrangement is there, means 2 layers which are alternate, they will be same. In that case, the arrangement is known as the hexagonal close pack. And in this case, there are some empty space. The empty space are known as voids. Now you can see the diagram. As I told you, packing in 2 dimension. So if 2 dimension packing is there, it is of 2 types. In first type, you will see the arrangement of particle is one over the another. See, all are in a straight line. All are in a straight line. So you can see the arrangement of particles are very regular and one next to another. So the layers are very same. We call it as the AAA type of arrangement. Now if you will take any of the particle, for example, you can see which is circulated with the square. We are taking this particle, center one, blue color. So 4 more particles are touching this one. If you join the neighboring particle, you will get a square. That's why this AA type of arrangement is known as square close packing. Square close packing. Now in the next one, if you will see second type. In second type, the particles are arranged in the space between the two particles. So in case of the second, that is hexagonal close pack arrangement, the particles are in between the depression of the first one, and as a result two layers are obtained. The sphere in the second row may be placed in the depression of the first row. This produces a row different from the first row. This arrangement is called as AB type of arrangement. In this arrangement, each sphere is touching 6 other sphere. You can see, for example, if the blue sphere, so you can see 6 sphere are touching each other. When you will join these 6 sphere, then you will get a hexagon. So the sphere in the second row may be placed in the depression. This produces a row different from the first row. Arrangement is known as ABAB arrangement, and in this arrangement each sphere is touching 6 other sphere. So the coordination number in this case will be 6. Coordination number means the nearest neighboring atom, and this arrangement is called two-dimensional hexagonal close packing. Second mode of packing is more efficient as more space is occupied by the sphere and empty space is less in the arrangement. You can see obviously the space in between. So if you will see the space in between, here you can see more space is there in between, and here less space is there. So the more efficient way is the second one. Three-dimensional packing. Three-dimensional close packing from the two-dimensional square close packing and from the two-dimensional hexagonal close packing. While placing the second square close packed layer above the first, we follow the same rule that was followed when one row was placed adjacent to the other. Second layer is placed over the first layer such that the spheres of the upper layer are exactly above those of the first layer. In this arrangement, spheres of both the layers are perfectly aligned and horizontal as well as vertical. Similarly, we may place more layers one above the other. If the arrangement of the sphere in the first layer is called A type, all the layers have the same arrangement. Thus, the lattice has AAA type of arrangement. Three-dimension close packing structure can be generated by placing layer one above the other. So this is the three-dimension view. You can see that how the three-dimension hexagonal close packing is possible. Wherever a sphere of the second layer is above the void of the first layer, you can see voids are there. Void means the space. So you can see the space here. Now the next particle will come over the void. So particle will arrange in this way, over the void, over the void, over the void. You can see in the downward diagram. So wherever sphere of the second layer is above the void of the first layer, a tetrahedral void is formed. You can do it with a tennis ball. Take 3 balls, arrange in this way, and keep the 4th ball above these 3. Then you will get a void inside, which we call as the tetrahedral void. Because a tetrahedron is formed when the center of these 4 spheres are joined. They have marked as T. You can see the T mark here. At other places, the triangular void in the second layer are above the triangular void in the first layer. and the triangular shape of these do not overlap. One of them has the apex of the triangle pointing upward and other downward. These voids are known as octahedral void. So you can imagine the void in this way. For example, if three spheres are there in this way, these are the particles. Now how the void will obtain? If the three more are there in between, so the void is there at the center, which we call as the tetrahedral void. So this tetrahedral void is obtained, octahedral void. Tetrahedral void is obtained when three particles and fourth one is above it. This is the tetrahedral void and this is the octahedral void. So tetrahedral void are obtained from the four particles and octahedral void are obtained from the six particles. In case, for example, number of close packed sphere is n. If n number of spheres are there, then tetrahedral void will be 2n and octahedral void will be n. Means octahedral void will be equal to the number of close packed spheres. You can see at the end. Tetrahedral and octahedral void, here you can see wherever the T is there, which is representing the tetrahedral void, and if O is there, so you can see the background also, because when you will see the background and upside circles, then only you can imagine the octahedral void. In both HCP and CCP methods of stacking, a sphere is in contact with the six other spheres in its own layer. It directly touches three spheres in the layer above and three spheres below. So, a sphere has 12 close neighbors. So, in this case, HCP and CCP, in both the cases, coordination number will be 12. Now, placing the third layer over the second layer. Here you can see the diagram so that you will come to know about the neighboring atom or the coordination number. In NCERT also diagram is given, so you have to do the imagination how the arrangement of the layer are possible. So for example, if void is there, so you imagine the void here. So how many particles are there? You can see 3, 6 and 3. So total 12 are there. So the coordination number will be 12. Tetrahedral void of the second layer may be covering by the sphere of the third layer. So the sphere of the third layer are exactly aligned with those of the first layer. Thus the pattern of the sphere is repeated in the alternate layer. This pattern is often written as ABAB pattern. And this type of arrangement you can see in magnesium metal, zinc metal. Now octahedral and tetrahedral void, you can have the view how they are present. This is the case of octahedral and downward is the case of the tetrahedral. So tetrahedral voids are formed by the 4. So here you can see how inside you can see the tetrahedral void because it is not visible from the outside. Third layer may be placed above the second layer, and when placed in this manner, the sphere of the third layer are not aligned with those of the first or second. So this is ABC type of arrangement. A layer, A, B, C. So this type of arrangement is there. Now packing efficiency in the simple cubic cell. In this derivation is there, but you have to learn the packing efficiency directly. In order packing, first of all, what is packing efficiency? Packing efficiency or packing fraction. So the percentage of total space filled by the particles is called packing efficiency. And when we say packing fraction, then the fraction of the total space filled is called packing fraction. Packing fraction is only the ratio of the volume occupied by the sphere upon total volume of the unit cell. but packing efficiency is the percentage. So when we are calculating the packing efficiency, we have to multiply by the 100. This is the formula to calculate the packing efficiency. So we should know the volume occupied by the sphere upon total volume of the unit cell. So imagine a unit cell. In this unit cell, A is the edge length. When you will see the edge length, you can see the yellow circle, edge length covering R and R, radius of first and radius of second. So A is equal to 2R. You can see here A equal to 2R. Now number of sphere per unit cell, you know it in the SCC, that is 8 into 1 by 8 equal to 1. Now volume occupied by the sphere. Volume of sphere, you know, 4 by 3 pi r cube, and volume of cube is A cube. So substitute the value 4 by 3 pi r cube divided by A cube. Now this A cube we can write as 2R cube because A equal to 2R. Now solve it. You will get 0.524 and multiply it by 100 because in formula 100 is there. Multiply it 100, you will get 52.4. So packing efficiency of SCC is 52.4. It means 100 minus 52.4 is equal to the empty space or the void percentage. Packing efficiency in body centered. So if you will see the body centered, so here it is covering diameter of the center one and radius of the two circle. So A can be calculated by the Pythagoras because this is the line and you have to find out the A. So A square plus A square is equal to FD square, side FD. So it is 2 square and under root will be equal to FD. You can see the calculation here. In triangle AFD, this AD is the edge length. DF is X, we have to calculate, and ED and EF, this you know, this is the 4R. How 4R? Center 1 2R, corner 1 RR. So total 4R. So in this way you will calculate A equal to 4R upon root 3. Now same formula you have to put volume of the sphere, that is 4 by 3 pi r cube upon A cube. Now this time A cube is equal to 4R upon root 3 whole cube. Solve it. When you will calculate, you will get 68%. Here 2 is multiplied because in body centered total contribution is 2. Packing efficiency in FCC or CCP or HCP, you can say. Again, you are watching the face and in this way these 3 circles you have to calculate. So the same way you will calculate the A, that is 4 by root 2R, and you will apply the formula volume occupied by the 4 sphere in the unit cell. So volume of sphere is 4 by 3 pi r cube. Total volume of the unit cell is 2 root 2 r cube. Now 4 is multiplied because in face centered in FCC contribution is 8 into 1 by 8 plus 6 into 1 by 2. So total contribution is 4. That's why we are multiplying here with 4. So percentage will be 74 and the void will be 100 minus 74. Now unit cell and the dimension. Directly you have to remember the formula. In this you have to find out the density, relation of the density. So volume of the unit cell is A cube. Mass of the unit cell is equal to number of unit cell into mass of each atom, where Z is the number of atom present in the unit cell. Small m is the mass of the single atom. So when we will calculate the density, you know density is equal to mass upon volume. So mass of unit cell will be Z into M and volume will be A cube into Avogadro number. So please remember the formula. This Zm upon A cube into Avogadro number. On this numericals are there. Now our next topic is defects in solid. This we will see in the next video. This is very important and mostly questions are coming in the exam. So defects in the solid is the last topic of the chapter because the other topics are cut in this year because of the COVID-19. So we will discuss only this defect, stoichiometric, non-stoichiometric and the impurity, which will be the last.